right, so we've called it Psychedelic Science 101. For the scientists in the room, it will be maybe not quite science, and for the rest of you, maybe too much science. I don't know. It depends on how much background knowledge you have. It's really history more than anything. So to give you a quick overview of the chemical space in sort of 5 seconds, all currently known psychedelics fall into one of three classes. So we have on the left here phenethylamines, and a prototypical example is mescaline that I've shown here from peyote cactus. In the center, you've got LSD 25, which is the ergoline class, so derived semi-synthetically from ergot fungus. And then on the right, you have tryptamine. So these are things like psilocybin shown here. So they're sort of your three major classes of psychedelics. There are many examples within each class. Tryptamines, for example, includes DMT, 5-MeO-DMT, and other things. There's a whole host of ergolines, and there's quite a few phenethylamines as well. So this is sort of chemical space that we're working in. And actually, it's a relatively recent area of pursuit. So although these natural drugs, such as psilocybin, have been used medicinally for a very long time in many indigenous cultures, Western medicine only rediscovered psychedelics quite recently. So this is Albert Hofmann here. He's a chemist who was working in Basel for Sandoz. He was actually looking for drugs for a number of different purposes derived from ergot, which had been sort of discovered in the decade before that. And he was doing systematic modifications of those drugs to come up with things that controlled hemostasis during childbirth and things like this. He accidentally made the 25th series in this library. It was a diethylamide. He believes he spilt some of the material on his fingers maybe, and it was transferred through his skin. But for that to be true, it would have been such an incredibly potent substance for the effects that he had. But basically, he accidentally had the world's first acid trip. He thought he was experiencing rapid and acute psychosis, went home, had a glass of milk, and it abated over time. But because he's a good scientist, he got really curious, and he tried to work back through his steps and work out if he could have been exposed to something. He knew ergots were quite potent. And he did an intentional self-experiment with what he thought would be the lowest possible dose that could have any effect, because this is such a profoundly potent substance. And he overshot it, basically. So we now know LSD is so potent that he'd done what would be quite a substantial dose. He continued to explore it, and he was just blown away by the sort of experience itself. So any of those here who are familiar with psychedelics, I probably don't need to say too much more. But he became a lifelong advocate of psychedelics for their sort of transformative power. And it's important to remember, we think about these as sort of illicit drugs, and we're reforming laws now. He branded LSD as Delicid, and it was used by psychiatrists in Europe for a long time, for a good 15 years before prohibition in the US eventually spread to other parts of the world. So these aren't illegal drugs that we're turning into medicines. These were things that were being used as medicines before they were sort of reactively banned. And I should say he lived, I was just reading up on his biography the other day, and he lived to a ripe old age of 102 and died in 2008, so, and was pretty well until he had a heart attack at 102. So I don't think drugs are necessarily bad for your health, at least not this class. So that was in 1943, middle of World War II, in Switzerland, famously neutral Switzerland. So a pretty unusual world context to be discovering such a powerful, transformative substance. And then things get even more interesting as a result of LSD and the discovery and all its application. An ethnopharmacologist, Gordon Wasson, shown here, was pretty wealthy because he was a banker as well, but he had this profound interest in mushrooms and ethnopharmacology around the world. And he'd always wondered about Mesoamerican, sort of pre-Columbian Mesoamerican depictions of mushroom stones, and whether there was some sort of medicinal use for these things. They appear just too frequently in Mesoamerican culture for them to be just a random chance. So he thought maybe there was some sort of medicinal type fungus that they were using, and he managed to head down to outside Oaxaca to meet up with Maria Sabina. So she's a Mazatec woman who was a curandera, and she'd actually been doing rituals with these mushrooms. I mean, this is a part of Mexico where people, it's so remote, people barely speak Spanish. These are truly indigenous people who've lived there forever, who have been using these substances even after Columbus and the Spaniards tried to wipe out the culture. So he went down there in 55. He wrote about this experience. It got published in Life magazine as an article, and that sort of blew open the floodgates for people getting really interested in the area. He ended working with Albert Hofmann to identify the material in mushrooms, psilocybin, that causes these effects, and basically this was sort of the catalyst for all psychedelic chemistry as we know it. And then a little bit later along comes this really interesting character, sort of personal hero of mine, and one of the reasons I got into chemistry. a guy named Alexander Shulgin. So he was working at Dow Chemical. He invented a really effective and commercially successful insecticide called Zectrin, and they gave him a really long leash as a result. And he said, you know, one of these things I'm super interested in is all these psychedelics that are appearing, what sort of structural features, you know, we talked about how a ligand interacts with the receptor and has an effect. He got interested in this relationship between structure and activity. So he's a bit of a molecular architect. He takes mescaline and he starts tweaking it. So one of the first things that he did was put a methyl group next to the nitrin there. So I've shown these changes in pink. And he noted that took the dose from 300 milligrams down to 100. So you've increased the potency and it changed the duration of action. It sort of extended it. He published a lot of this work, and at that point Dow said, yeah, we're not too happy having Dow's name on these journal articles. So he set up a lab in the East Bay at his home, and that's where a lot of this work was done over the following years. If you take the 3, 4, 5 oxygen atoms there, the O's around the ring, and you just move one round a spot, you get a compound that's about 5 times more potent again, and with an even longer duration of action. And then if you change out one of the methoxy groups at the 4 position for a bromine or other halogens, that fundamentally changes the subjective nature of the experience. Also makes the thing extremely potent, about 1 milligram. So LSD is fully active at about a quarter of that, and it's one of the most potent drugs we know of. And the duration gets pretty unpleasant. 30 hours of a full psychedelic experience doesn't sound that enjoyable. But he was just very diligent, very systematic in his efforts. You'll note I've got doses here, and the reason we have doses and not concentrations is because he was testing them on himself, starting at very low doses and working his way up. And for materials that show promise, he's actually also the grandfather of MDMA, and some of you will know that substance. But many of his compounds ended up being used underground by psychiatrists and clinicians in the Bay for counselling and for all sorts of other things. Also died in quite good health, famously very old, and he's probably tried more psychedelic substances than anyone on earth. So this concept of structure-activity relationships is sort of pretty crucial to medicinal chemistry as an enterprise, and it's very crucial to what Psylo is doing. So we're not testing these things on ourselves, we're testing them in cellular systems, and we now have a whole host of modern scientific tools that we can use to modify psilocybin and explore the effects of those changes in a very systematic way. And it's a super exciting time. If I can get this video to play. Oh, I don't know how to right-click in a Mac, so it won't. It probably won't loop. But this is an interesting depiction. So one of the benefits of the psychedelic resurgence happening now, instead of continuing 30 years ago, is that we have all of the modern tools of molecular biology, of neuroscience, functional imaging in human patients. Like, we have this incredible wealth of technology that we can bring to bear on these problems. This structure is actually the 5-HT2A receptor that I mentioned previously, bound to LSD. So this was resolved by isolating the receptor, bombarding it with X-ray radiation, looking at the diffraction pattern, and reconstructing the image at the single atom level. So this is a molecular detail, a molecular granular structure of LSD. People can do dynamic studies, look at it going into the orthosteric pocket, look at how it moves around sort of in real time, slowed down dramatically, and then leave the receptor. And you can actually do a whole lot of structure-based design, meaning that you can computationally dock ligands that we design with people like Asher into this very same receptor and have an informed guess about what sort of profile you might get before you even start making things. So one of the areas that we plan to differentiate ourselves on is bringing virtual screening, high throughput virtual screening to the table to discover new chemotypes that have very strong composition of matter claims and might offer even better chemotypes than psilocybin itself.
Can I ask a question?
Yeah, go for it.
So you said it comes into the pocket and leaves
Yeah.
Is that right?
This is a static image that we've just rotated,
Right,
but yeah,
right.
you can model it.
So it comes into the pocket and it leaves. So it comes in and it's functional and then it leaves. It's not broken down and your body's assimilating some part of it that makes it magical.
No.
It leaves at some point because
Yeah. So that's known as ligand kinetics. It's the rate at which a drug binds to a receptor, induces a conformational change, and then leaves the receptor. And the parts you're talking about where it's broken down and does other things, that's metabolic enzymes elsewhere in the body. So this is at the site of action in certain neurons in the brain that is primarily responsible for the effects that we think of as the subjective effects of LSD.
What's interesting in this case is that the pocket is, well, at least with LSD, it is in such a way that LSD stays in
Yeah.
other compounds live. And this explains to some extent the long duration of action of LSD compared to other compounds.
It's got a little receptor lid that just kind of closes down and stops it getting out too easily. Yeah, it's pretty wild. Yes. Oh, there is so much happening biochemically, yeah. No, it's a super good question. We're interested in a few different things, including this aspect of signaling bias. So at a molecular level, this small drug, relatively small drug, binds to the much larger protein. It's a very dynamic but also subtle process that changes parts of these helices, these coils here. It just changes the conformation of those ever so slightly. And if they swing a little bit one way, you get recruitment of these sort of secondary effector proteins. And if it swings a little bit the other way, you get a different set of proteins. So it's not, even though we do this in vitro screen that's only looking at one outcome, there's actually a lot going on here. And we're setting up a beta-arrestin assay is what it's called, to look at some of these other signaling pathways as well. Yeah, it's very, very complex. We present it in a simple, reductive way, but it's obviously very, very complex, yeah. Biology is hard. Chemistry is relatively easy these days. Biology's never got any easier. Yep. Awesome.
Another random question. When you're looking at the receptors and you're saying, hey, this potential compound that we discovered might do X, and X might be relieve anxiety, deal with depression, are you determining that by the receptor that it's working on or some other factor? Like, how do you kind of go, do you look at this compound, say the one that you're about to patent, right? Are you kind of like, we think this is going to do X? Do you kind of know what you think it's going to do?
Yeah, we're following both the preclinical and clinical streams of evidence as they emerge. And so one of the things we're aiming to do sort of immediately is to make a shorter acting psilocybin-like molecule. Psilocybin's got a duration of sort of 6 to 8 hours. Given that it's a pretty intensive psychotherapy adjunct where it requires 2 therapists to be there for that entire duration, we foresee something that has maybe a duration of action of 2 hours or 3 hours being superior for its brevity, perhaps, in some of those indications. In terms of what you might use it for, in that particular case, it's foreseeable that it might just displace psilocybin as a primary method of choice for a lot of different indications. So in other cases, you mentioned things like anxiety, sometimes not our key targets of interest right now for these receptor subtypes, but some other one we were talking today with our pharmacologist about 5-HT1A, that's a historical target for anxiety. There are anxiolytics that target that site. So we're going to be guided by the data as it comes in, and we're following all of the clinical developments to see what sort of indications might be suitable for a lot of the things we're developing. Thanks so much.